You know, this is all calculated. Every field is whole thing. It's unit, yeah, this whole unit is calculated. That's all. Papers. Yes, but they give a notebook. That's the first part. This is all calc.
All right, so we're on page 2. Today we're going to be working on these types of problems that where we're given a function that has a definite integral in it, and we have to basically interpret how to get this information from this graph. So this is the F graph right here. Okay, so okay. So the graph of function f is shown consisting of a semicircle and 3 line segments. Let g be the function given by g of x is equal to the antiderivative of f of t. So this is not the g graph, okay? This is the f graph. And we talked about how first we want to kind of establish the relationship between g and f. G is the integral of f. Okay? So that means the integral of f means that g is sitting at a level above f, okay? Which means that if I do g prime would have to take this and bring it down 1 level. So it's the f of x graph. So what that really means is that this f of x graph is the g prime graph. Okay. So if you understand that, then you're basically looking at the derivative graph for g. Okay, this is the derivative graph for g. So anytime, and then we also talked about how if g prime is f, then g double prime also is going to require to drop down 1 level, so f becomes f prime. So that's the relationship that we're going to be working on with this graph in front of us. That if I want to find anything involving g, I have to basically pull the area under the f graph. Anytime I'm looking for a g prime value, I'll be looking at this f graph. And anytime I'm looking for a g double prime, I have to think of this as the slope. Okay. All right. And also we're going to pull some information from first semester as well as we go through this. Okay, so it's always going to follow this this relationship. Any questions with that? Okay. So they're kind of staggered, right? So g is the antiderivative of f, g prime is f, and g double prime is f prime. Okay. They're staggered in that relationship. So part B says find g of 0. Okay, so g of 0. All we do is we just plug 0 into the formula that's provided for us. Okay. So g of 0 equals . All right, so over here, g of 0. We just follow whatever the rule says from -3 to x, right? So I'll replace my upper bound with 0 because that's where the x is. So we just have to figure out the area between -3 and 0, okay? And then also between the graph and the x-axis. Now, keep in mind that anytime we're looking for area, make sure that you're looking in the correct region. We don't want to be creating different, I know you see different shapes in front of you, but you're only looking at what's between the graph and the x-axis. So I'm going to just shade in lightly all the potential places that we could look at. Okay, we don't want to be looking at any other place. I mean, it's possible that you're drawing, you may draw different shapes along the y-axis, but it's always what's between the graph and the x-axis. Okay, so those are the only regions you're looking at. I want to make sure that that's established. We're never looking at anything beyond what I just shaded in. Okay, so we're looking at just the region between -3 and 0. So between -3 and 0. Now, this is technically a trapezoid, but if you want to deal with trapezoids, you can just create easier shapes for you to work with, right? So I can see a triangle on top of a rectangle. If I find those two areas, then I have that region between -3 and 0. Okay, so this rectangle, what's the area of this rectangle here? 3. And what's the area of the triangle on top of it? 1/2 base times height. So 1/2 3 times 2, which is 1.5. And it's all above the x-axis. So the depth integral from -3 to 0 of f of t is equal to what? What's that full region added up together? 1.5, yeah. All right. So we're always relying on the definition to help us through what we're going to try to add up. Next up, find G prime of 0. So let's just look at the link between G and F. G prime of 0 is just f of 0. And f of 0 is just looking for an ordered pair that lies on this f graph. So what's f of 0 equal to? What's the y value of the f graph at 0? 1. Yep, it's just that point that f of 0 equals 1. Okay, G double prime of -1. To find G double prime -1, we just find f prime of 1. F prime of -1. So what does that mean? F prime of -1 means I'll look for the what on the f graph at -1? Slope, right? So -1 is here. Right? You may not know where that point is, but you know that slope is going to be the same all the way through. So if I just pick 2 points at the end, I can just find the slope of the line, right? This line segment. So change in y over change in x. I can count down 1 over 3. So what's my slope? -1/3. Okay. So if you're given this problem, there's 3 things that you want to be able to do. You want to be able to find the area, if it's asking you for it, or the order pair, or the slope. Okay, so those are the 3 relationships. Okay, we're going to pull in some first semester review here below, but any questions so far? Okay, we'll definitely get more practice with this over the next few days. I know we're going to start the next unit tomorrow, but we'll still have the second half of class tomorrow and Thursday to continue to review these topics. Yes. The integral notation, that's right.
So the problem there, one notation was usually by those points. It's like G0,
I have to give you some starting point to begin with. There is a different variation of this, but on this test, I'll give you this setup. Okay. But yeah, there is a different way of asking this question, but I'll get to that later. Okay. But this is a popular setup for an FRQ. They like to do this to also see if students understand the idea of derivative graphs. Okay, so part C, find the values of x in the open interval from -5 to 4 at which g attains a relative max. So we don't have the g graph in front of us, but we do have the g prime graph in front of us. Does that make sense? Okay, because it says that this f graph in front of us is the g prime. So if we want to find relative max, we can't just look at this graph and say, oh, that's -3 and at 2, because this is the f graph, but this is also the g prime graph. So it's not asking where the f graph attains a relative max, it's asking for where the g graph attains relative max. So we go back to this relationship here, g prime is equal to f of x, and we just have to understand that this is the g prime graph. So think back on first semester. We labeled our derivative graph accordingly. Above the x-axis means where our graph is physically rising. Below the graph, below the x-axis indicates where our g graph is falling. Wherever it lands on the x-axis is slope 0. All right, so let's create a slope sine line for our g prime. I'll put it here so that I can see both the graph. Okay. So we're going from -5 to 4. What's my critical point? Okay. Critical point is wherever my slope is 0, right? So where's my slope 0? -4 and 1. Yeah. So -4, 1, 3. Okay, so those are the potential relative max, relative mins. I just want to get everything on this sine line. So what's happening between -5 and -4? Decreasing, because below the x-axis. Between -4 and 1, increasing, because it's above the x-axis. We don't want to look at the rise and fall, just look at the location. Is it above or below the x-axis? It's clearly above. Between 1 and 3, still above. And then between 3 and 4. So look at the arrows here. It's falling, then it rises, it levels off, it rises, and then it falls again. So where's my relative max? 3, yeah. So a little bit of review from first semester, being able to look at a derivative graph and be able to pull information from that derivative graph. And then part D, find the absolute minimum. Okay, so this is a concept with EBT. Okay, so also first semester material, but within the context of integrals that we have to understand here. Absolute minimum. So if I want to find absolute max, absolute min, what candidates do we have to consider? You remember? Absolute max, absolute min, we have to consider what? Endpoints. Yeah, because the endpoint could land as a max or min, and then also relative max. Right? We don't have to. And a relative min. We don't have to consider relative max because there's no chance that relative max can ever be the highest point, the lowest point, right? There's no chance that a relative max. So it's only asking for absolute minimum. So you only have to consider endpoints and relative min. So we'll consider -5, we'll consider 4, and we'll also consider what? -4, right? So only 3 points we got to consider. We need to consider g of -5. So we'll test endpoints and relative mix. Now, if the problem is asking for find absolute max and absolute min, then we have to test endpoints, relative mins, and relative max. But here we can save a little bit of time. We can just disregard relative max and just focus on what we need to focus on. So we'll test g of -5. We'll test g of 4, and we'll test g of -4. Okay, let's do -5 first. G of -5 equals. Now we have to go back to our definition, right? This is the definition that is going to help get us an ordered pair. G of x is integral from -3 to x of f of t dt. So we have to look for the area under the graph between -3 and -5. Okay, does that make sense? Why we have to always use that -3 there? Why is that? Because yeah, it's in the definition, right? So we just have to use whatever is given to us, right? We don't have to create anything. We just have to follow the rules. Okay. Now we're reading the graph. We're trying to find the area reading the graph, but there's something that I want you to notice. You notice anything about the bounds? Yeah, it's a little backwards, right? And normally I would say it's not a big deal if you're doing definite integral and you're plugging your upper and lower bound, it'll work out the same way, but you're trying to read a graph. So if you want to read a graph, we want to read from left to right. Otherwise, everything is backwards. Otherwise, above is negative and below is positive, and it feels weird. So what can I do to flip the bounds to adjust here? Make it negative, yeah. And that way we can just add up the regions without having to worry about keeping track of the negatives and positives or changing the signs in our heads, right? That negative is taken care of. We just have to remember to account for that negative when we get back to our problem. So between -5 and -3, let's go here. -5 and -3 is below the x-axis, 1/2 base times height. 1/2 1 times 2 is 1. So the area is 1, but it's below the x-axis, so we'll have to assign it a -1. So I'm going to put -1 in place of this, but there's already a negative in front. So we keep track of our negatives, and we know that g of -5 is 1. So we don't see the g of x graph, but if we were to plot some points, we know this point will live on that g graph. Oh, wait, my bad. I missed something here. I said from -5 to -3. Sorry. So this area here is also 1. So -1 plus 1 is 0. My bad. So there's a negative in front of that 0, but in this case, it's not going to matter because -0 is still 0. Okay, next up, g of -4. Integral from -3 to -4. Again, what do you notice about the bounds? Yeah, it's backwards, right? So I'm going to flip the bounds. And I should have to worry about the area between -4 and -3. Between -4 and -3, it's above the x-axis. We already found that region. So +1. But there's a negative that I pulled out in front, so -1. Okay, G of 4 is a little messier because we have to go all the way out to the right side of the graph, and there's some different shapes that we have to worry about here. So from -3 to 4, this one, is this in order? Yes. So we just have to worry about the region from -3 to 4. So -3 all the way out to 4. So, well, we already have all this taken care of, so we can skip all this. Now over here. That in itself is not a geometric shape, but is there something that we can do to get to this little region using shapes that we know? Yeah, it's a rectangle minus a what? Semicircle, right? So if you were to imagine a rectangle there, and if you were to subtract the semicircle, what's left are these little triangular gaps. Okay. So off to the side, I'll put this over here. The area of that region is a rectangle minus a semicircle. So a rectangle is length times width. So this imaginary rectangle here is width of 2, height of 1. A semicircle is 1/2 pi r squared. What's the radius of the semicircle? 1. So 2 minus pi over 2. Now it's all sitting above the x-axis, so we can just leave it in this form, but we just know that that region is going to be just 2 minus pi over 2. It looks messy, but we just have to leave it in that form. Now this here, a triangle, 1/2, 1 times 1, that's 1/2. And here is also 1/2, but it's below the x-axis, so negative 1/2. So now I want to add everything together from -3 to 4. So I have 4.5 plus 2 minus pi over 2, and I can ignore the 1/2 minus 1/2 because I know that which is 0 out. So 4.5 plus 2. So 6.5 minus pi over 2. Now pi seems strange, but we can just imagine what to replace pi in our heads so we can just have some idea. Pi is close to what? 3, right? So 6.5 minus 1.5 is around 5. Yeah. Yeah, that's true. You can.
Okay.
You can. But I just want to prepare you for, if this was part of a non-calculator section, then you do want to be able to have some idea that you don't feel lost when you see pi. You can just, I can just put a 3. It's close enough to get a ballpark value. So between these 3 numbers these are the candidates, right? So what is the absolute minimum? What's the lowest number that you see here? -1. Yep. So that's it. Absolute minimum is -1. And when it asks you for absolute minimum, you only care about the y value. You don't have to go back and say what the x value is. And it says show work and justify. And this is a common wording that you're going to see on the AP exam. With extreme value theorem, you don't have to provide any words. If you go through the steps and show that you are testing endpoints and your critical point, that is justification. Okay. Some of the other problems, some of the other theorems require more words and phrasing. But the nice thing with EVT is that if you just show your work and if you just show that you are testing the points that you're supposed to test, then you will get full credit. Okay, part E is also first semester review. Find all the values at which the graph of G has a point of inflection. So point of inflection, remember, this is the G prime graph. So point of inflection, how do we find the point of inflection looking at the first derivative graph? Okay, but how do we find points of inflection off of the derivative graph? Peaks and valleys. Yeah, peaks and valleys. Okay. Obviously, the peaks and valleys is not where the point inflection is on the original graph, but that's where it's going to be located on the derivative graph. So -3, 1, and 2. Okay. So we know points of inflection is at -3, 1, and 2. But I just want to fill out the rest of this concavity sign line, just for our frame of reference in case the problem is asking for concave up and concave down. So if you're looking at the derivative graph, first derivative graph, how do you find the intervals where the graph is concave up? Slope, right? Slope is positive, right? Don't look at the curvature, look at the slope. So here, positive slope, concave up, concave down, concave up, concave down. Yeah, so it's going to keep interchanging between the two concavities. Also, we have justification that these truly are points of inflection because we are getting the change in concavities in each of these intervals. Oh, for points of inflection? No, we don't. But if I wouldn't ask you for this, but if you were to look for it, how would you go about finding the y value? Plug it into the g of x formula. The g of x formula, basically you have to go through that area procedure and find that y value that way. So on the test, you'll see a problem very similar to this. Okay, so we'll practice more with this, but I feel once you understand this concept and you know what to do, you will see, if you understand this process, you shouldn't have any surprises on the test because you're going to go through the same process. And these problems do tend to show up in one form or another on the AP exam. That's why I really want to go through a problem like this. Okay. Okay, let's do another one of these. Right. I feel like these are the ones that that just takes more practice than the others. So let's see if we can fit in one more of these and if we can do a Riemann sums. Okay, so we have, again, this relationship here, which indicates that F and G are staggered, right? What you're looking in front of you is the F graph, but it's not the G graph. But let's just go ahead and build all the relationships. So if G is sitting at a level above F, then G prime must be what? Good. So it's F, but then there's second theorem going on. So this X will get inserted in here. So yeah, so we can say F of X. Which means that G double prime is what? F prime. Okay, so you can just always establish that relationship, especially if they give you that F and G relationship to begin with. All right, so number one, part A, find G of 2. So G of 2, we look at our relationship and we just insert the X wherever they tell us to put it. So from -2 to 2, we're just looking at this region, right? Semicircle, 1/2 pi r squared. What's the radius here? Two, yep. So 4/2 is 2 pi, but any adjustments, it's below the x-axis, so negative, yep. And also I didn't end up flipping the balance because it's already in order, right? Smaller to larger, it's good. We don't have to make any adjustment, okay? G of -4. Okay, is adjustment needed here? Yes, so I'm gonna go ahead and flip the balance, change the sign. Between -4 and -2. I'm looking at this little triangle region here. 1/2 base times height. What's the area there? 1, but below the x-axis, so -1. So I got to keep track of that additional negative and the negative in front because of the flip. So it ends up being +1. Okay, questions? Okay, G of 6. Just follow whatever the rule is given to you and put X where it belongs. -2 to 6. I already have this figured out, so I know that's -2 pi. And then from 2 to 6, that's just a triangle, 1/2 base times height. It's above the x-axis. What's the area there? 4. So I have to include this -2 pi, right? So -2 pi plus 4 or 4 minus 2 pi. I have to add up the two regions, right? The semicircle and the triangle. Yeah, you can leave it this form, yeah. Okay, next up, find G prime of 4. G prime of 4, well, let's look at the relationship here. G prime of 4 is F of 4. So F of 4, that should be easy. That's just the order pair. What's F of 4 equal to? 2, Y value. All right, G prime of -2. Again, we look at our relationship there. Is F of -2. F of -2, look at the order pair. Okay, G double prime of 5, and G double prime of 5 is F prime of 5. F prime of 5 means you're going to find the what? The slope, right? So you just have to figure out, I mean, it's along this line here. So if I just find 2 points here and find the slope, down to over 2, what's my slope of this line? -1. Let me just do a few more examples of G double primes, just so I can, yeah, just to make sure that you're comfortable with it. So what if I asked you for G double prime of 0? Basically asking you for the slope, right? What's the slope there? 0. Okay. What about G double prime of 2? the slope here? Undefined. Yeah, any sharp turn is an undefined slope. Okay. So sharp turns are undefined slope. Do you know where else undefined slope is going to occur? Yeah, peaks. Sharp turns, where else? Two more places. Endpoints. Endpoints also slope undefined. Okay. Okay. So I want to make sure that we just understand how to interpret through these types of problems. You're either look at the area between the graph and the x-axis, or you're pulling the y-value, or you're pulling the slope, right? Depending on which level you're working on. Yeah. No, because then you would need a formula to help you get there, right? So if it's a geometric shape, it's meant for you to be able to find it easily, either 0, undefined, or along a diagonal line. Yeah. Okay, for what value of x is g increasing? Okay, so remember, we're not asking for where the f graph is increasing. We're asking where the g graph is increasing. So this is not the g graph. This is the g prime graph. Okay. So let's keep reminding ourselves, this is the g prime graph. We can't just look at this and say, oh, it's increasing here, it's increasing here, right? This is the derivative graph. Yes. Yeah. If I'm giving you this relationship and I'm giving you f, you're always looking at a g prime graph. Okay. So let's build our slope sine line. Where is our critical point? -2 and 2. Okay. Oh, I'm sorry. Those are the endpoints. -2 and 2. Right, because that's where my slope zeros will occur, and those are my potential relative max, relative min. Okay, what's happening between -4 and -2? Below the x-axis, don't look at the fact that it's rising, look at the fact that it's below the x-axis. So decreasing between -2 and 2, below the x-axis, decreasing. Between 2 and 6, above the x-axis, decreasing. So based off these arrows, we should be able to identify what's happening. Where's our g graph increasing? From 2 to 6. Yeah. Okay, where's g decreasing? Good. Always separate. Okay, always separate to be on the safe side. Find x values for all points of inflection. So points of inflection, we're looking at the derivative graph. How do we find points of inflection? Peaks and values. Okay, so there's 3 of them, right? I have -2, 0, 4. Now we want to fill in the rest of the blanks with concave up, concave down information. So what's happening here? Concave up because it's rising. Concave down. concave up, concave down. Yeah, so it's going to keep alternating. Okay, find the absolute extrema of G. So that means I'm looking for both absolute max and what? Absolute min. So where are my, what am I considering then? Endpoints and all relative max, relative min. Okay, actually, we don't have to test -2. Why is that? Yeah, it's neither a relative max, relative min, so we can get away without testing this one. There's no chance a non-relative max, relative min can ever be absolute extrema. So you only have to test 3 points here: -4, 2, and 6. And how do we test these points? We plug them into the G of X formula. This is going to help get us the physical y values of the G graph that we don't see in front of us. That way we can compare the y values. I'm sorry. Oh, yes. Yeah, that's true. Yeah, we did. So G of, so that saves us some time. G of -4 is 1. G of 2 is -2 pi, which if we wanted to just give a ballpark value, that's around what? -6, right? Just so we can have something to compare with, okay? And then G of 6. Okay, so that's good. We found all this now, but if we didn't, if it wasn't already asked of us, then you have to go back and do it yourself. Okay, so 4 minus 2 pi. Let's do a ballpark value. I know you have the calculator, but I just want to practice it without a calculator. This is around what? 2 times 3 is 6. 4 minus 6 is around -2. So therefore, absolute max is, what's the highest y value? 1. Absolute min is -6, but you'll say -2 pi just to be exact. Okay. Okay. You guys feel okay about this? Okay. So you will see a problem exactly like this in terms of the steps. Okay, so that's good. That's 1 out of 3. We've already done the other 2, but we'll continue to practice them. Even though we start the new unit, we'll still practice them. I'll have help sessions Wednesday morning, Thursday morning, and Friday morning. But typically, I feel students do better on this because it's very similar to what you're doing. There's less this fitting to a puzzle like use of C. Okay, come up, get your phones. Yeah.
Page rusher.
Yep.
Oh, Mr. Yeah.